Hi all, it's a pleasure to be speaking to you today from my son's bedroom. A bit weird, but I'm enjoying the idea of actually talking to some people today. So Jurassic Park, the original film, came out 27 years ago this week, which makes us feel a little bit old in some senses. But the sort of public impact that this has had on our understanding of science still goes on to this day. In fact, a lot of what you think about paleontology probably comes from movies and popular culture like this. In the sense, you might think of a paleontologist delicately brushing a bone, sticking out of the mud. But in this talk, I wanted to talk to you about the reality of modern paleoscience and how it's much more than that, and the cutting edge of science that's taking place at the University of Manchester and how that relates to our teaching. Some of this short presentation is borrowed from some of the first year teaching content, which I deliver as well. So I mean, obviously the first year content is very, very varied, but this is just to give an idea about some of the things that are coming up in the first year. And exactly as Rian said, we're talking about the wide variety of training in different areas. So first of all, the premise of Jurassic Park, just to give you a quick reminder. Dinosaur blood was extracted from mosquitoes preserved in amber from 100 million years ago. This DNA was combined with frog DNA, and those DNA sequences were used to clone and rear dinosaurs. But of course, in reality, sorry to dispel this myth for you, DNA is far too fragile. Experiments trying to extract DNA from much younger amber, as the University of Manchester has shown that to be not possible. And the oldest DNA that we can actually reliably extract is about 800,000 years old. So given that dinosaurs are over 60 million years ago, that's not going to happen. However, the modern science of paleontology can actually serve a really interesting role in helping us bring the dead back to life. Using a combination of techniques from physics and chemistry and biology, we can reconstruct past animals, and we can test hypotheses about evolution, about how life on Earth changes, and important processes about Earth system processes as well. In this nature, paleontology is interdisciplinary in the sense it cuts across multiple ways, much in the same way that Rian described geochemistry and the application that it can do is there. So I'm going to work through just a couple of these examples of physics, chemistry, and biology. In this first physics example, this is Victoria, a member of staff here at Manchester, scanning a large sauropod dinosaur with lasers to try and reconstruct a digital model to make virtual skeletons. When you take that, you can use this information and apply it to things like computer simulations, as Bill Sellers has done at the University of Manchester. Here is one of this Diplodocus to try and reconstruct its walking, and here's Tyrannosaurus Rex in a computer simulation. And when we do that, we find out that T-Rex was actually unlikely to be a predator because it couldn't run and it wouldn't have been an effective thing at chasing. So this is an interesting question, not only because we're aiming to reconstruct life more accurately, but also because it's testing important questions about the limits of evolution. How big can animals get and still function? Those sorts of questions can only be addressed with paleontology. Of course, this uses a lot of computer modeling and simulations and physics. Here's an example from chemistry. What did these animals look like? Well, this is a bird, which you may be able to see some feathers. It's a really great fossil from the Cretaceous. But what did they actually look like? What colors did these organisms originally have? Well, to do that, we can take these things to this particle accelerator, as the team at Manchester took this to the Stanford Accelerator in California, with the high-powered X-rays we use to analyze the chemistry of it. And then we can reconstruct the distribution of chemical elements, but also the composition and distribution of those elements in terms of how they were coordinated in their original life. And from that, we can begin to reconstruct the patterns of melanosomes and black and white feather patterns in this particular organism to say that actually it had a black body and white feathers, and we can therefore infer things about its ecology and evolution. So we can begin to reconstruct this using really detailed examples. As is this example here with this odd dinosaur, which was from a team, not from Manchester, a different one, where it had this ginger and white stripes on its tail. So we can begin to understand a bit about its camouflage and interaction with other organisms at the time. Also, we can use examples from biology. So this is an example, again, from a research at the University of Manchester. Here was an unknown bone fragment from the Arctic of Canada, about near Greenland and near the Arctic Sea. It was too fragmentary to understand what it was, but the team at Mike Buckley and others were able to extract the original collagen protein from this bone and reconstruct its sequence in terms of its amino acids. So this is a really cutting-edge technique in helping us identify the actual genetics of these fossil organisms. And when we do that, we're able to identify it as belonging to a camel. And this allows us to see that the camels existed in Arctic Canada 3.5 million years ago. Camels actually originated in North America and spread to South America and Europe and Africa through these routes. But now we can understand when that happened and this involves different things to do with biology and geochemistry, but also climate change in terms of what the distribution of these organisms and evolution of these organisms was. But also this technique can be applied to look at ancient DNA in all sorts of cases to establish that these two Egyptian mummies at the Manchester Museum were two brothers. We can look at mammoths and ancient, but it might actually be theoretically possible to bring back a mammoth. The woolly mammoths have been extinct for a while, but here the genome has now been reconstructed, and we might be able to use, in theory, DNA sequences from the mammoth and Indian elephants to genetically engineer or clone a mammoth. Now, this brings us back to the original premise about whether that's ethically appropriate, but I'm not going to answer that question today. I'll leave that up to you. But it could have all sorts of implications, given that humans may be responsible for the extinctions of mammoths, and they may play an important role of tackling climate change. They could engineer the environment in the Arctic tundra. But that's a bigger question than we have time to think about today. So, Earth and planetary sciences with paleobiology is quite interdisciplinary. We're using physics, chemistry, and biology, and you don't need to have all of those, as Rian points out. We give you that training in the first year. Through these different things which Rian has discussed, we give this idea that in the first year we give you the training. In the second year you have options and specialisms, and in the third year you can take those specialisms in any particular direction you want. So you get training in data handling and a wide range of analytical skills, from one end, from the geological and biological, to things like computer programming or experiments or geological fieldwork. It's up to you to make your path on the paleobiology pathway. Should leave you well placed in the different directions. But as I pointed out at the beginning, I kind of dismissed this idea that paleontology was just still delicately extracting dinosaur bones from mud. But of course that's still necessary, and that is still happening. Indeed, the University of Manchester is involved in a massive Mission Jurassic project, a multi-million-dollar project in Wyoming to dig up fossils. So here is some of the team, some of the students that have been out there. I have a short video and we'll just explain what's going on with this project, which involves the University of Manchester and the Indianapolis Children's Museum, as well as people in Europe. That may not work because my internet connection has seemingly gone dodgy, but we don't need to explain, see the details too much. The idea is that they've been out there digging up these new exciting sites using modern technology to extract all the information with drone technology and geochemistry, a massive project to try and extract these dinosaur giants. Or not. Perhaps you're not invited right now because my internet connection is not working. We'll leave that. Here is some of the students from the University of Manchester that have been sent out and given the opportunity over the summer projects to go and dig up those fossils, and they had a great time out there. Obviously that's on hiatus this summer, but hopefully that'll be returning for 2021. So that gives you an idea about the realities of Jurassic Park and how actually, whilst we might not be able to bring dinosaurs back from the Jurassic, we can nevertheless use interesting different technologies and sciences to understand and bring the dead back to life, and how paleontology involves people from all sorts of different disciplines. I started out as a biologist, but we also have archaeologists and geochemists and geologists on the team as well. And I will pass it back to Rian to ask questions or move on to the next talk.